Welcome to Lesson 4, the Photoelectric Effect. This is one of the clearest pieces of evidence that light behaves as a particle. Here's the plan for today. Let's start with a question. What actually is a metal? Picture a regular lattice of positive metal ions sitting in what we call a sea of delocalized electrons. These are free to move around. That's metallic bonding. What we want to do in this experiment is flick some of those electrons off the surface using light, but the electrons are held in by the attraction to the positive ions, so first we have to overcome that attraction. We can overcome this attraction using photons. Remember our photon equation, energy equals h times F. Planck's constant, h, is fixed, so the energy of a photon depends only on its frequency. The higher the frequency, the more energetic the photon. That's why ultraviolet, X-rays and gamma rays carry so much more energy than visible or infrared light. Enough, in fact, to damage the DNA in your cells. Hold on to that link. Higher frequency means more energy. Here's the classical demonstration, the gold leaf electroscope. We shine light on a metal plate connected to a thin gold leaf. When electrons are ejected from the plate, we're left with a positive charge. So electrons at the bottom, near the gold leaf, move up to the plate to counteract the positive charge. The plate and the leaf are left positively charged, so they repel each other, and the gold leaf visibly rises. That rising leaf is our signal that electrons are coming off. Now, two experimental facts that are the whole point of this. First, below a certain frequency of light, no electrons are emitted at all. It doesn't matter how bright, how intense the light is. You could blast it all day and nothing happens. But above that frequency, electrons come off immediately, and there's no delay while they build up energy. This immediate effect is important later, as we can sort of think of it as a small piece of light meets an individual electron and frees it. These facts point to a threshold frequency and a matching minimum energy needed to free an electron. We call that minimum energy the work function with the symbol phi. It's the energy required to just liberate an electron from the surface of the metal. Now the key equation. The energy of the incoming photon, hf, splits into two parts. Some of it, the work function phi, is spent freeing the electron. Whatever is left over becomes the maximum kinetic energy of the ejected electron. We call this the maximum kinetic energy because some electrons might be further down in the surface, and as they're liberated by a photon, they lose energy by hitting into the large metal atoms on the way out. So hf equals phi plus the maximum kinetic energy, and if you set the kinetic energy to 0, the bare minimum to escape, you get the threshold frequency. F0 equals phi over h. So why does this experiment prove that light acts as a particle? The trick is, it's the instant emission that gives it away. In the particle picture, a single photon dumps all of its energy into a single electron in one go. So if that photon has enough energy, the electron is liberated immediately. If we had a wave in contrast, this would spread its energy across the whole surface of the metal, and electrons would have to slowly accumulate enough energy to escape. This would mean you'd expect a time delay, but experimentally we never see this delay, so light here is behaving as particles. Here's a metaphor that I like. It's not like shaking the whole block until every electron gradually rattles loose at once. It's like flicking the electrons off one at a time. One photon corresponds to one electron. Now let's think about putting this in a circuit. If we have the electrons being liberated and they move to a collecting place, then this will create current flow. Here's an important piece, the stopping voltage. Say we applied a reverse voltage across these two plates. The ejected electrons would have to do work against an electric field. And at the right voltage, even the electrons with the highest kinetic energy would be stopped completely. At that point, all of the kinetic energy has gone into that work. So the maximum kinetic energy E equals the charge times the stopping voltage. That just comes from work equals charge times voltage. You must know how to put this onto a graph. The graph of maximum kinetic energy against frequency. It's a straight line. The gradient of that line is Planck's constant h. It crosses the frequency axis at the threshold frequency f0, and if you extend it back, the y-intercept is minus the work function. If you can draw and label that graph correctly, you can answer most photoelectric effect questions. That's the end of the video. Next time we'll look at how atoms emit light through energy levels. I hope you enjoyed the video and check out my tutoring page in the description.